Hey guys, so I know your homework isn't due for a couple more days, but I had requests to get the homework videos out a little early for you, so you have this for your midterm. So here it is. Just remember with the midterm you have a full week, so you have plenty of time to take it and study and make sure you understand everything. Don't forget, I have my open office hours, student hours, whatever you want to call them, on Wednesdays. So I'm still doing those. You are still welcome to come by if you have questions. So we're going to start with the Chapter 14 homework questions. Number 1, we're told the concentration of an acid in a solution is 2.8 times larger than the concentration of its conjugate base, and it has a pH of 4.7, and we want to know what the pKa is. So we can start by writing down what we know, and we can write it in some other ways. We can say the concentration of acid is equal to 2.8 the concentration of base. Okay, or we can also say HA, meaning acid, equals 2.8 times A minus for the base. And we know our pH is equal to 4.7. And so this is screaming for us to use the Henderson-Hasselbalch equation, which tells us that pH is equal to pKa plus the log of base concentration divided by the log of your acid concentration. So we know, first kind of zooming in on this, we know we can rewrite this as saying the log of base of A minus over, we know that HA is equal to 2.8 times A minus. So those are going to cancel out. So now that gives us the log of 1 over 2.8. So see, we didn't even need actual concentrations. Being given that relationship between the two is all the information that we actually need there. And so the log of 1 over 2.8 is equal to negative 0.447. So we can rewrite this equation to solve for pKa. Oops, sorry, not negative 4. I got ahead of myself. So rewriting this, pKa is equal to pH minus our log of 1 over 2.8. Oh, that is what it equals. I got ahead of myself getting ahead of myself? I don't know. Well, the pH is 4.7 minus the log of negative 2.8 is, or 1 over 2.8 is negative 0.447. So we see minus negative, that gives us a plus. So adding those up, we get pH is 5.147. So that's a nice quick one using Henderson-Hasselbalch. Pretty straightforward. Our next question, we're told a solution is made by adding 0.34 moles of lithium hydroxide in enough water to form 2 liters of solution, and we want to calculate the pH. So lithium hydroxide is a strong base. So this one is straight up figuring out our concentration of hydroxide, and then from there we can get our pH. So we're told we have 0.34 moles in 2 liters of solution. And the concentration of hydroxide, okay, is going to be equal to the concentration of lithium hydroxide, as it's a 1-to-1 ratio. So we are told that there are 0.34 moles of LiOH. And we could just go ahead and write that that's 1 mole of OH minus for every 1 mole of LiOH. Moles LiOH cancel. And then that is dissolved in 2 liters of solution, so that means we have to divide it by 2 liters. And so from that we get 0.17 molar for our concentration of hydroxide. So now you have hydroxide, you can either use hydroxide times hydronium equals 1 times 10 to the negative 14th, or you do what I do, which I calculate POH, and then I use that to calculate pH. It doesn't matter how you do it. So POH is equal to the negative log of hydroxide. So that's the negative log of 0.17, which is 0.770. This is a very basic solution. So pH is equal to 14 minus POH. So that's 14 minus 0.770. So you get 13.23 for your pH. So this is a very basic solution. Our next question. In a 0.03 molar solution of chlorous acid, what percent of the acid is ionized to the chlorous anion, ClO2-? And we're told Ka is 1.1 times 10 to the negative 2. So this is our first problem where we're going to need an ice diagram, because it gives us a clue telling us a Ka. We're going to have an equilibrium happening here. So one thing we can first write, since it's telling us we're looking at percent ionization, and just so we don't forget that's what we're looking for, we can just kind of write to the side that percent ionization is equal to the concentration of H3O plus divided by our initial concentration of acid times 100. So just so we don't forget. Oops. Okay, so for this reaction, you might have to look up some formulas. Chlorous acid is HClO2. So that aqueous, and we're reacting it with water, which is liquid. And that's in equilibrium with hydronium, H3O plus, aqueous, plus the chlorous anion, ClO2 minus, aqueous. So let's set up an ice table. One of the first things is water goes away. It's a liquid. Its concentration is 1. And then some of the other things we know, that we're starting with 0.03 molar chlorous acid. We can go ahead and approximate our acid starting concentration, our H3O concentration, to 0, because it's so low with the autoionization of water, it's not going to really make a difference. And then the chlorous anion starts at 0. So the chlorous acid is going to lose some X and the others are going to gain. So at equilibrium, we have 0.03 minus X, X, and X. So our equation for Ka is going to be the concentration of H3O plus times ClO minus divided by the concentration of HClO2. So this then is X times X over 0.03 minus X. Now this Ka is too big for us to go ahead and assume that X is much less than 0.03. So we need to leave this as such in the equation. It needs to stay 0.03 minus X. We cannot get rid of it. I'm just going to write it prettier. Okay, so now we need to do some algebra. So we know Ka, I'm just going to rewrite it like this, 0.11 is equal to X squared over 0.03 minus X. Multiply both sides by 0.03 minus X, and so you get that X squared is equal to 0.00033 minus 0.011x. Let's go put everything on the same side to get us a quadratic. So then this tells us that X squared plus 0.011x minus 0.00033 is equal to 0. So go ahead and use a quadratic equation solver or the quadratic equation itself. Like I said, I found some great quadratic solvers online, so you just plug in for your numbers for A, B, and C and hit solve. Saves a lot of time. So the root that ends up working is X equals 0.01348 molar, and this is equal to our concentration of H3O plus. It's also equal to our concentration of chlorous anion. So as you see from the equilibrium, they're both equal to X. But we are not done yet. The question wants percent, and we want ionization percent. So now we need to go back to that original equation, percent ionization is equal to the concentration of H3O, which is 0.01348, divided by the original concentration of acid, 0.03, times 100, and this gets 44.9%. So this would be a great example of something that might be a test question. You've got your ice table that you need to do, you've got a Ka, you need to solve for something, and then there's that one little extra step. So make sure that you're reading the questions well and completely when you're taking your test. All right, number 4. We are told an aqueous solution containing 0.22 molar of an unknown base has a measured pH equal to 7.52, and we want the value of pKb for the unknown base. So we can kind of write down what we know so far. We know we have 0.22 molar of this base. And we have a pH equal to 7.52, and we want pKa, or pKb, sorry, not pKa. And so the general equation for a base is you have some base that's aqueous reacting with water. And in our equilibrium, that gives us base with an extra hydrogen with a positive charge plus OH minus. We're generating hydroxide. So let's set up an ice table for this. Water doesn't work in the ice table because it's a liquid. So the starting concentration of our base is 0.22 molar, and it's losing some X amount to end with 0.22 minus X. For our BH plus, we're going to approximate, that one starts at 0, and hydroxide we approximate to 0, plus X, X, X. So let's write our equation for Kb. Kb is equal to our concentration of BH plus times OH minus divided by our concentration of base. So plugging in what we know, we have X times X over 0.22 minus X. Okay. We are looking for Kb. So let's just keep this Kb equation in the back of our heads because we really can't do anything. We don't know what X is and we don't know what Kb is. So we need to first figure out what X is. And we can start by doing that by using this pH we're given. So pH is equal to 7.52. And we know that pH plus pOH is equal to 14. So our pOH is equal to 14 minus our pH of 7.52. So that gives us a pOH of 6.48, and we can use that to find our hydroxide concentration now. Hydroxide is equal to 10 to the negative pOH, which is negative 6.48. So our hydroxide concentration is 3.31 times 10 to the negative 7th molar. So this is now equal also to our BH plus in our equation. Now this number though is very, very small. So we can also go ahead, this is X, and we can say that this is way smaller than 0.22. So now in our Kb equation, we can go ahead and get rid of that 0.22. So, but now that we have this to substitute in to Kb, so we know that Kb is equal to X squared, which is 3.31 times 10 to the negative 7th squared divided by 0.22, since we got rid of that minus X. And then once you punch all that into your calculator, you get a Kb equal to 4.98 times 10 to the negative 13 power. Very, very small Kb. All right, number 5, determine the pH of a 0.11 molar aqueous solution of ammonia, and we're given our Kb value. So let's just go ahead and just write the reaction for ammonia. NH3 aqueous plus water. And that's going to go to form NH4 plus and OH minus. So let's set up our ice table for this equilibrium. We started with 0.11 molar ammonia, losing some X, and 0 NH4, about 0 hydroxide, adding some X, X, X. So we know that Kb is equal to the concentration of ammonium, times OH minus, hydroxide, over ammonia. So that is X times X is X squared over 0.11 minus X. And you technically can use your assumption here. I didn't in this case just because I'm complicated like that. I don't know why I didn't, but we'll just go with it. So this ends up becoming, equals to 1.8 times 10 to the negative fifth. Oops, let me check something. Okay. And so then we end up getting a quadratic of X squared plus 1.8. Oops, what did I do? Oh, okay, I just forgot to write something. Okay, 1.8 times 10 to the negative fifth X plus 1.98 times 10 to the negative 6 is equal to 0. So you get that X is equal to 0.00140 molar, which is the amount for ammonium and for hydroxide. And then we want pH, and since this is the concentration of hydroxide, we can use this to get pOH, which is the negative log of 0.00140, and that's 2.85. And then pH will be 14 minus that. So our pH is equal to 11.15, a basic solution. Give it some Ugg boots and a pumpkin spice latte, because she basic. It sounds really good right now. I wish it was pumpkin spice season still. Okay, nonetheless, next question. This is the last one for chapter 14. Lactic acid is a monoprotic acid that dissociates in aqueous solution. If a solution containing 0.50 molar lactic acid is 1.66% dissociated to ionic form, calculate the value of Ka for lactic acid. All right, so we're starting off by being given a percent ionization, which seems kind of weird, right? But that's okay. It's going to be very helpful to us, I promise. So we know that 1.66% is saying 1.66 per 100 parts dissociated for lactic acid. And so that is equal to some concentration of hydronium, because that's what we're talking about with the with percent ionization. We're looking at the amount of hydronium divided by the amount of acid, right? And in this case, lactic acid is our acid, and we're told that it's 0.50 molar. So we have H3. Oh, I didn't mean to do that. Okay, let's try this again. So that means we have H3O plus over 0.50. So now we can solve for our hydronium concentration from this by multiplying both sides by 0.5, and we get that H3O plus is equal to 0.0083 molar. So now we actually have our hydronium concentration, which is good. Now let's set up our reaction and an ice table and see where this is going to come into play. So we know lactic acid HC3H5O3 and water. While I'm writing this, by the way, lactic acid is what your muscles make when you work out, and that's what makes you sore. So one assignment that I like to do with my students when I do Chem 1 is I have them actually write a paper talking about how chemistry relates to their major, whatever their major may be, because it really is essential science. And a lot of times I have physical therapy majors come up to me and say, no, it doesn't have anything to do with what I'm studying. And I have to point out, yeah, it does. Lactic acid. And then they can go from there. So, ice table. ICE, we started off with 0.50 molar lactic acid. We lost some X to get 0.50 minus X. About 0 hydronium, we gained some X. 0 of the ion, gaining some X. But hey, we know what this X is for hydronium. We just solved for it. And look, hydronium is equal to the ion concentration. So hey, look, we can substitute it in everywhere. So now we know that hydronium and the lactic acid ion are equal to 0.0083 molar. And then we know that the lactic acid concentration is equal to 0.50 minus X, which is 0.4917 molar. So now we know that Ka is equal to the concentration of H3O plus times C3H5O3 minus divided by the concentration of HC3H5O3. And so that is 0.0083 squared, which is 6.889 times 10 to the negative fifth, divided by 0.4917, and you get 1.40 times 10 to the negative fourth power for Ka. So that's another good one for a test question, because you've got that acid-base reaction, you've got something a little out of the box with using percent ionization to get your amount of hydronium, which I think is a really creative thing to do. So that does it for chapter 14. Your next video is on its way.